a method called regularization. In this entire course, we will visit this topic twice. Once now, just to give you a feeling of what regularizations are, and then another time in part 4, where we talk about learning theory. Then we will revisit this topic and see what do we mean to have regularization towards the problem of bias variance trade-off. Okay? So why do we need regularization and what they are? Let's look at this outline to give you an idea. So last time in lecture number 1, we talked about linear regression, the simplest possible model that you can ever find in a machine learning problem. Okay? So it's a linear model. It's very simple. That also corresponds to what I call the prediction of that pipeline. And now today we want to look at another component of this pipeline, which is the loss function. We do have a loss function last time, and the loss function is the square loss function. And we're pretty happy about the square loss function because we can take derivatives, set it to 0, we can get analytic forms. So everything looks fine. Now today we want to look at another angle of this loss function. Can we add something to this square loss function so that we can have a solution that could be better? Now better, I need to define what is better, right? So it is a topic about loss function, and this loss function idea, by putting regularization, is also very common even in the world of deep neural networks today, because remember in the deep neural network, if you have done any experiment about deep neural network, you always put some regularizations to your parameters, okay, so that they behave well. Now, even if you don't put, the optimizers behind these libraries, they have already done some implicit regularizations for you. For otherwise, your solution could just easily diverge. Okay, so what is the outline of today's lecture in particular? We want to study the topic of regularization, which is about constraining the solution. And there are two parts of this lecture. One is on the thing called ridge regression, which is one type of regularization, and it's fairly easy to analyze. The other one is called the LASSO regression, a more popular regression nowadays when the convex optimization techniques becomes mature. So we will visit these two types of regularizations, and they are pretty common if you flip any machine learning literature nowadays. Okay, so first let's look at the topic of ridge regularization. This ridge regularization is extremely simple. You look at the loss function, which is a square loss function between a theta and y, and I add one more term, which is the 2 norm square of theta, okay, and then put a lambda here. Now this lambda is called the regularization parameter, and you can tune this parameter, make it bigger or smaller, and it has different effects. Now, by putting this regularization term, which is the theta 2 norm square, you do something to the solution, okay? So this is still a quadratic equation, and that means I can take derivative and set it to 0, and I should be able to get a similar form as what we did last time. So let's do that, and you can see that in the derivation I'm showing you in the middle, there is indeed just taking the derivative, setting it to 0, and you get a solution. And the solution is shown in the bottom, and it says that instead of having just A transpose, A inverse, and A transpose, I will have an additional term of lambda I, right? Where does this lambda I come from? You go back to the derivation, you see that there's a 2 lambda theta that goes into the second line of the proof. That's how this lambda I come into the equation. So we can ask, what is the role of this lambda I? Can you give me some interpretation of this lambda I? There are multiple ways of looking at this problem, and I'm going to give you one perspective. There is another perspective, which is the probabilistic perspective, which you can find it in the appendix of this lecture slide. Okay. In there, you can see the maximum likelihood estimation problem, and then you can also see a problem called the maximum a posterior estimation problem, and you can see how this regularization is playing a role of being a prior in the Bayesian setting. Okay. Now, in the following few slides, I want to spend time and talk just from the pure linear algebra perspective, just as to follow up what we discussed last time. Okay. So let's look at the eigen decomposition of this matrix A transpose A. Okay, by eigen decomposition, I mean that I compute a orthogonal transform U, and then I also find the diagonal matrix S of that matrix. Okay, so if I do the eigen decomposition of this matrix A transpose A, now it's on A transpose A, not A. Okay, A could be a tall matrix, it could be a fat matrix. But then A transpose A is always a square matrix. I just want to make it clear. If you do the eigen decomposition on A transpose A, you will get this decomposition of U, S, and U transpose. And if you look into the elements along the diagonal, you realize that they are all positives. Well, they're all non-negatives. Why are they non-negatives? Well, you will never get negative values on that because you have A transpose A. You do the A twice, right? So it's the magnitude square of the eigenvalues of the A matrix. So now you have all these non-negative eigenvalues. And of course, depending on your feature vectors, if they are correlated, you might end up having some zero eigenvalues. So the diagonal matrix of your S matrix will have something, and then you will have a zero. You may have more zeros. You may have a bunch of zeros. Okay? So that would be the structure of your S matrix. Now, when you add lambda times identity, what will happen is what I'm showing you at the bottom. Okay? So think about you have a diagonal matrix, but then for all the diagonal elements, you add a lambda. Now we ask, what is that matrix? They're all positive, as long as you make the lambda positive. Do you guys follow me? Okay? So then you ask, what is the implication? Well, previously, since you have zeros in your eigenvalue matrix, you cannot invert that. 1 over 0, you get infinity. That means you will blow up the matrix. But now, since you have lambda, and lambda is positive, and so that all the elements along the diagonals, they are positive. So you can easily invert that. So that can help you solve the problem where you have rank deficiencies. Okay? So that's just one approach to solve this rank deficiency problem. And you can easily show that by doing so. The matrix A transpose A plus the lambda I is a positive definite matrix. In contrast to without the lambda I, it is a positive semi-definite matrix. So there is a role being played by this lambda I. So then we can ask, what is the role of this lambda? Well, if I tune up this lambda, what lambda should I use? Well, let's look at this expression. If you make the lambda extremely small, you send it to 0, then basically what you're saying is that, look at this loss function. You have both the A theta minus y squared term and also the lambda theta squared term here. You put lambda to 0, that means you really don't care about the regularization. And therefore, you go back to the original formulation by having just the A theta minus y term. And so you will get the original pseudo-inverse solution. Now, on the other extreme, if I set the lambda to infinity, extremely large, so that your first term, your theta term, you don't care about anymore, then what you will have? Well, you will just have minimization over lambda times the theta square. And you have a solution there, which is 0. Okay? Now, does it make sense? Well, you can go to the first equation I'm showing you in the slide, which is the pseudo-inverse solution with the lambda put into the place. You make the lambda to 0, you get the original pseudo-inverse. You make the lambda go into infinity, you do get 0 because that infinity will go to the denominator. Right? So this lambda is a trade-off knob between how much trust you want to put into the theta term and how much trust you want to put into a prior knowledge about the theta. So 2 norm squared is nothing too special. It's just a very handy way of regularizing the magnitude of your theta. So think about that. If you choose a theta that has some entries that are extremely large in terms of magnitude, you're not going to be happy in this formulation because you're adding the data term and also your solution term. And if your solution has a magnitude really, really big, you're going to penalize that. And therefore, the solution that comes out of this regularized linear regression, the norm of that solution has to be constrained. That's how you can get a solution that is smaller in some sense. Now, if you put the regularization too strong, of course, you will get a trivial solution of 0. You can plot the behavior between the data term and also the regularization term on this curve. It's called the Pareto frontier curve. And on this curve, you will plot this data term value versus the regularization term value. Okay? And there is one sweet spot where you want your algorithm to operate at. Okay? Now, which spot is that? We don't know. You need to tell me what spot you want to operate at. And there are different ways of approaching that spot. Now, I want to make it clear, it's not at the corner of that L-shaped curve. It's not necessarily that, okay? So I'm going to spend some time talking about this issue. But before that, let me comment on what is the benefit of using a ridge regression compared to not using a ridge regression from a little bit more formal way. So we can assume that your observation vector y is indeed coming from some ground truth theta star times your A, and then there's some residual error, you call it E. Okay, let's make that assumption first. Your observation comes from that model. And what I want to do is to give you some equations, a list of equations, just to convince you that with the ridge regression, you can indeed do better according to the metric that I'm going to introduce to you. Okay? So let's do some algebra. It's not too hard. Okay, just follow the equations up there. You look at the theta hat according to the pseudo-inverse equation, and you just expand it out. And what do you get? You will get an equation that's showing you in the third line of the slide, which is the theta star plus the pseudo-inverse times E. Now, what is E? E is your residue. It's the error that you impose in your model. Okay, I assume that you do have an E there. Now, let's look at this interesting thing. If your E is 0, you can pretty much ignore the second term, right? If E is 0, you can ignore the second term. Now, if you have any E, since you're taking the inverse of A transpose A, what are you going to do? You're going to amplify the E's. Depending on how small your eigenvalues are. If your eigenvalues are close to 0, you're going to amplify the E infinitely large. Is that a clear point? Right? Everyone follows me? So this amplification is extremely important. It's so powerful that it will ruin your calculation if you have any perturbation in your model. And in fact, you can run some additional analysis. You can assume that the E is a zero mean Gaussian vector with a variance sigma square. You can show that the expectation of the theta hat is indeed theta star, but your covariance matrix will become the sigma squared times the inverse of that A transpose A matrix. And apparently, if you have a 0 eigenvalue, you're going to get 1 over the 0. You have infinity in your inverse. Okay? And so you can further show that the mean square error, which is the sum of the bias term and also the variance term, something that we will come across later. Okay? You can show that the mean square error is actually the trace of this inversion matrix. All right. So this is the problem of the vanilla linear regression. That if you have linear dependent columns, you just try to invert that without using any pseudo-inverse tricks, that would be the problem. You're going to amplify the noise infinitely large. It's super sensitive to any perturbation in your system. When you implement the ridge regression by having just that small lambda I into your equation, you change the entire scenario. Okay? This is, again, a list of equations, which I'm not going to ask you to just derive them. If you're interested in all these derivations, there is one reference I put into the reading list. You can refer to that paper, that they have all the derivations proved in details. So what people have shown is that if you put the lambda into your equation, then the expectation of the lambda will be given by this equation. The covariance becomes that, the mean square becomes that. It's a big equation. However, if you look at the mean square error, the final result, where people have shown is that for an appropriately chosen lambda, your mean square error of this ridge regression is guaranteed to be strictly less than the mean square error of not having a lambda. Okay? Now, of course, you need to choose a lambda, but as long as you have chosen a good lambda, it's guaranteed that the ridge regression will perform better than the vanilla linear regression. Okay? So that is the power of this ridge regression. It regulates the solution because you make this positive semi-definite matrix into positive definite so that you can do the inversion, and you also constrain the mean square error. If you make the lambda extremely big, then I'm sorry, you're violating the assumption that I'm putting in this theorem. Then of course you're not guaranteed to be better. Okay? In the extreme, you set lambda to infinity, you get 0. Of course, how can that be better than a vanilla regression? So there's a constraint on the range of lambda that you need to put. Okay, so I want to comment on the following 3 optimization problems. Okay, these 3 problems, they are representing different perspectives of the same problem. The ridge regression that we have been looking at is the first problem, where you try to minimize the sum of both the data term and also the regularization term with the parameter lambda. And let me call the solution as a theta subscript lambda, because if you change the lambda, the solution will change. The second optimization I'm showing you here is minimize the data function subject to the constraint that your 2 norm square, your regularization, is upper bounded by some constant alpha. Okay? And then the third problem is that you minimize the norm of the regularization, okay? And then you put a constraint that your data term has to be upper bounded by epsilon. It turns out that all these problems, they are equivalent. How can that be possible? Well, it is possible when you have chosen the correct tuple of lambda, alpha, and epsilon. Okay? Now, you can do this exercise at home. You can take the derivative, set it to 0 for the first problem, get a solution. For the second problem, you can try to use the Lagrangian approach, which we will comment on next time. You can do some a Lagrangian on the second problem, get a solution, and do the same thing for the third problem. And for the appropriately chosen pairs, tuples of lambda, alpha, and epsilon, they're the same. They're exactly the same. Okay? The solutions of these 3 problems are exactly the same. Now, why do I want to introduce these 3 different perspectives of the same problem? Well, because in a practical situation, you will land on one of the 3, depending on what problems you have. Okay? Let me give you an example. I have some data collected, okay? And then I want my solution to really best fit this data set. So I really care about the fitting error. So why do I care? Well, you want to minimize the error of A, theta, and Y. So that would be the minimization problem. Okay, minimize the 2 norm square between, say, A, theta, and Y. Data term minimization. And then you say that I'm okay with the regularization term, just don't make it too big. Okay? And I can tolerate the magnitude to be up to alpha. That would be the second problem. You see that? Okay? You want to minimize your data term with the constraint that your regularization, that your solution has to have a magnitude no bigger than alpha. You can pose that constraint because you are the designer. You can say, I don't want the regression coefficients to be too big. If that is the case, you will have an alpha. You choose an alpha. And since the lambda problem and the alpha problem, they are equivalent when you have chosen the correct pair of alpha and lambda, you can just solve the second problem. Right? You can just solve the second problem, and you can guarantee that there is correspondingly there is a lambda that will solve the first problem. And that is very handy because you go back to the L curve I'm showing you, that will correspond to one operating point on the L curve, because if you go back to here, that tells you, hey, this is my upper bound on my solution norm square, and you cannot go beyond that. That would be it, okay? So that would define an operating point on that curve, and then that would be the corresponding lambda. So you can choose a lambda according to that way. What else can you do? Well, you can say, okay, I want to work with the third problem. Well, the third problem says that I really just want to minimize the magnitude of my regression coefficients, okay? And I'm okay to tolerate certain levels of error in my data fidelity. Now, then you are landing on the third problem. And then the third problem says to solve it, give me an epsilon that you can tolerate. Solve the third problem. You can get to the solution of the first problem by finding the corresponding lambda, right? So there are lots of discussions on how do I choose the lambda. Okay, you have a lambda. How do I choose the lambda? It really goes back to the problem that you have in hand, right? So you can ask yourself, what would be the physical problem that I am really interested in? Now, of course, you can also say, I really don't know anything about my data sets. Okay, I'm just a data scientist. I don't have the domain knowledge about this data set. There are alternative approaches. It's called the cross-validation approach. Okay, so that means you have all these data sets, and then you leave one out, and then you do the calculation and see which one gives you a better prediction. Okay, so we'll come to this idea of cross-validation or generalized cross-validation later on in this semester. Okay, I just want to mention that there are plenty of methods out there that can help you choose a lambda. Now, of course, as an engineer, if you're just a programmer, it's also okay to say that just do try and error. Okay, it never feel too shameful to do try and error, because by trying and error a few times, you will know how bad the solutions that you have and how good the solutions you have. That will also work, okay, if you're in a training stage, okay? As long as you do not use the testing data to choose the parameter, you're fine, okay? To have a strict discipline between the training data and testing data. That's rule number one in machine learning. Never try to use the testing data in any sense when you design your algorithm, all right? Okay. Any questions so far for the first part on ridge regression? Yes? The question is this a bias versus variance trade-off? If you refer to here, it is. Okay? What do I mean by bias? Bias is how close is your theta hat compared to your theta star. Okay? And then what is the variance? Variance is the trace of the covariance matrix. And so there is an intrinsic trade-off between bias and variance here, as you can see from the formula. And therefore, you want to choose a right lambda to minimize the mean square error, which is the sum of the bias and the variance. Okay? So if you do not choose a right lambda, you will suffer, because you can have a very, very big variance, although you have some small bias, or the other way around, you have a strong bias, but you have a very small variance.